Assalamu alaikum wa rahmatullahi wa barakatuh. I am Al-Dailami with matrix number 1622847. Today our group will present the randomized algorithm. This is our table of contents. Introduction. Randomized algorithm is a technique that uses source of randomness. Randomized algorithm is the purpose of it is for reduce the running time complexity, memory use, or space complexity in standard algorithm. And this algorithm works by generating a random number within a specified range of numbers and making decision based on numbers value. And there is a lot of usage for randomized algorithm, and some of it is such as flipping a coin or drawing a card and so on. For algorithms examples, we have some algorithms examples, and the first is minimum cut algorithm, Las Vegas and Monte Carlo algorithm, binary space partitioning algorithm, and probabilistic recurrence algorithm. I will explain the first and the second algorithm. Minimum cut of widgeted graph is defined as a minimum sum of widgets of at least one edges that divided the graph into two groups were removed from the graph. Machteld Store and Frank Wanger proposed an algorithm in 1995 to find the minimum cut in undirected widgeted graph. The algorithm works on method of shrink the graph by merging the most tightly connected vertex until only one node is left in the graph, and for each step performed, the widget of the merged cut is sorted in a list. The minimum value in the list would be minimum cut value of the graph. And this is the graph, and it can be seen in this image. At most left, it is a whole graph, and the at most right, the only two states and three edges from the whole graph. And this is because we applying a cursor bisect algorithm. And this algorithm, in each execution of the outer loop, the algorithm repeats the inner loop until only two nodes remain. The corresponding cut is obtained. The runtime of execution is n, and n denotes the number of vertices after n times execution of the outer loop. We output the minimum cut among all the results. The second algorithm. It's basically two algorithms, Las Vegas and Monte Carlo. We'll start with Las Vegas. These algorithms always produce the correct or optimum result. The time complexity of these algorithms is based on random value, and time complexity is evaluated as the expected value. For example, randomized quick sort always sort an input array, and the expected worst case time for complexity of quick sort is n log n. For random quick sort, it is a sub algorithm from Las Vegas algorithm. The idea of the algorithm is quick sort algorithm is to choose a random pivot to sort the array with other items inside it. the code of algorithm includes two loops. We can assume that the outer loop is I and the inner loop is G. The outer loop exists to choose a random pivot. However, the inner loop is to scan the elements and compare them to the item of the index I until the array is sorted. The worst case time complexity is n power of 2. And Monte Carlo algorithm. These algorithms produce correct or optimal result with some probability. They have deterministic running time, and it's generally easier to find out worst case time complexity. For example, this implementation of Karger's algorithm produce a minimum cut with probability greater than or equal to 1 divided by n squared, and n is a number of vertices. The worst case time complexity is n. Another example is Vermeer method for primarily testing. Regarding the algorithm, it is used Karger's algorithm that we already explained in the time cut algorithm. This is my part, and my friend will explain the rest algorithms and also the conclusion. And assalamu alaikum wa rahmatullahi wa barakatuh.
Assalamu alaikum. My name is Khamis. So I'm going to be presenting on the binary space partitioning. So what is that? Basically, it is a technique for recursively partitioning space into two arc sets by utilizing hyperplanes as allotments, or as to assign partitions to get the hyperplanes. So it was created with regards to 3D PC illustrations and is often used in first-person shooter games. In addition, game engines using BSP trees will be used alongside a Z buffer to correctly merge movable objects such as doors and characters onto the background scene. Since it's from front to back, so yeah, it reduces the CPU cycles and therefore is faster and more efficient as compared to Painter's algorithm. We'll get into that in a bit. So for the third one here, we have the different utilizations, which includes performing mathematical activities with shapes in computer-aided design, the CAD, crash recognition in advanced mechanics and 3D computer games, beam following, and many more that include the treatment of complex spatial scenes. So over here, we have the process of creating a BSP tree. Over here, we just create a arbitrary partition. Create a hop, for example, we have a partition over here, and we have a root node A. So after that, we find the front and the back. So for the front over here, as you can see, step 2 is C. So you put it on the right side. Everything behind A, we put it on the left, which is B here. We named it C and B. So over here in the third step, we create another partition over here, and then we have E, in front of B is E, and behind B is D. For the third one over here, we create another partition. We have in front of D is G, and behind D is F, and so on. So moving on to the next slide, we have the generation of the BSP tree. So the authoritative utilization of a BSP tree is for delivering polygons that are double-sided, that is without back face separating with the Painter's algorithm. So the Painter's algorithm basically is an algorithm that is usually like the opposite of BSP. So it starts from back to front. All the shapes will be drawn behind first, and then the front will come afterwards. So what that will do is actually it will increase the CPU cycles, and it will create overdrawing, which is less efficient. Less efficient than compared to the BSP. The tree is developed from an unsorted rundown of the relative multitude of polygons in a scene. This diagram shows that the use of this algorithm is converting a list of lines of polygons into a BSP tree. Alright, so we start off like this. Okay, so we go to the next. Yeah, so this is the final representation of the BSP tree after completing all the steps. We have 8 steps, so I will explain it right now. So when you create it, we have a line over here, nodes in front of A will be B2, D2, D3, and C2. Therefore, you can see it over here. And the ones behind A is D1, B1, and C1, as you can see it over here. So when we create another line, when we want to go to B2, we create another line over here, like this. And the ones in front of B2 is D2, and the ones behind B2 is C2 and D3. So when you go over here to C2, you can see that in front of C2 is only D3. It's drawn over here. And then moving on to the other side, we have B1. So when you have a line over here, B1, in front of it is D1, and then behind it is C1. As you can see here, the final number of polygons or lines in a tree is often larger than the original list. The BSP tree is traversed in a linear time, in a sequential way, in a request dictated by the specific capacity of the tree, and to draw a polygon P effectively necessitates that all polygons behind the plane P lies and should be drawn first, after the polygon P, and finally the polygons in front of P. So number one, if the current node is a leaf node, render the polygons at the current node. Otherwise, if the viewing location V is in front of the current node, first foremost we render the child BSP tree containing polygons behind the current node. Then we render the polygons at the current node, and last but not least, we render the child BSP tree containing the polygons in front of the current node. Otherwise, if the viewing location V is behind the current node, we render the BSP tree containing polygons in front of the current node, and then at the current node, and last but not least, behind the current node. So as you can see, it's the opposite. If the viewing location is behind the current node, we start with the front of the current node, then the current, and last but not least, the behind the current node. So otherwise, the viewing location V must be exactly on the plane associated with the current node. Then render the child BSP tree containing polygons in front of the current node and behind the current node. You don't need to render the polygons at the current node. So as you can see, it's over here. That's all from me. Brother Sohaib will continue from here.